Hey, welcome to another episode of Following Science, where we delve into the mysteries of the universe and uncover the secrets behind the phenomena that shape our understanding of the cosmos. I'm your host, Rutu Ruparel, and today we're going to be decoding one of the most powerful and awe-inspiring events in the universe, the supernova explosion. In this episode, we're going to explore the importance and the nature of supernovae, the science behind their explosive power, the methods used to study them, their impact on the universe, and what the future holds for the supernova research. So, let's dive right in. A supernova marks the explosive death of a star, a cataclysmic event that can outshine entire galaxies and radiate more energy than our sun will in its entire lifetime. But what exactly is the supernova, and why is it so important to study these stellar explosions? Now, supernovae are not just spectacular light shows in the cosmos, they are fundamental to our understanding of the astrophysics. These explosions signal the death of a star, but they also pave the way for new stars to form, recycle matter into the interstellar medium, and create heavy elements that are essential for planets and life. Now, humans have explored and observed supernovae for centuries. One of the earliest recorded supernovae, SN 1054, was noted by Chinese astronomers in 1054 AD. This event left behind the famous Crab Nebula, a beautiful remnant that is still studied today. Now, fast forward to 1572, when Danish astronomer Tycho Brahe observed a new star in the night sky, which we now know as the supernova. These early records were crucial in providing the first clues about the transient and explosive nature of these stellar phenomena. The observations of SN 1054 and Tycho's supernova were among the first to challenge the ancient belief that the heavens were unchanging. They provided concrete evidence that stars do indeed have life cycles, which can end in very dramatic fashions. Now, these early supernovae paved the way for modern astrophysics, giving scientists a rare opportunity to study the universe's dynamic and violent side. Now, supernovae are characterized into two main types based on their spectral properties and mechanisms that drive the explosion. Let's break it down. Type 1 supernovae lack hydrogen lines in their spectra. These are further subdivided into Type 1a, Type 1b, and Type 1c. Type 1a supernovae occur in the binary systems where a white dwarf accelerates material from its companion star until it reaches a critical mass and explodes. Type 1b and Type 1c result from the collapse of massive stars that have lost their outer hydrogen layers. On the other hand, Type 2 supernovae exhibit hydrogen lines in their spectra. These occur from the core collapse of massive stars that still retain their hydrogen envelopes. When the core of a star runs out of a nuclear fuel, it collapses under its own gravity, leading to a dramatic increase in its temperature and pressure that ignites a runaway nuclear reaction. Now, to understand the process of a supernova explosion, we need to look at the life cycle of a star. Stars like our sun will end their lives as white dwarfs, but more massive stars go out with a bang. In the cores of massive stars, nuclear fusion creates heavier and heavier elements, from hydrogen to helium, carbon, oxygen, and so on, all up to iron. Iron is unique because fusing iron doesn't release energy. Instead, it absorbs it. When the star accumulates an iron core, it has reached the end of a life cycle. Now, without the outward pressure from fusion to counteract gravity, the iron core collapses within seconds. The collapse triggers a dramatic increase in temperature and pressure, leading to a runaway nuclear reaction that causes the outer layers of the star to be violently ejected into space. This is the core collapse supernova. Let's break down the steps of a core collapse supernova in more detail. Initially, the star undergoes a phase of hydrostatic equilibrium, where the inward force of gravity is balanced by the outward pressure from nuclear fusion in the core. As the star ages, it exhausts its hydrogen fuel and begins to fuse heavier elements in the successive layers around the core. Once the core reaches iron, fusion no longer produces energy. The lack of outward pressure then causes the core to collapse under gravity, reaching temperatures of over 1,000,000,000 degrees Kelvin. The core collapse halts abruptly when the neutrons in the core become degenerate, creating a neutron star, or in some cases, collapsing further into a black hole. The infalling outer layers rebound off the stiffened core, creating a shockwave that propagates outward, ejecting the star's outer layers into space. This is the explosive event that we observe as the supernova. Now, supernovae act as cosmic alchemists, creating elements heavier than iron. These heavy elements, such as gold, silver, and uranium, are scattered into space, enriching the interstellar medium. This process of nucleosynthesis in the supernovae is essential for the chemical complexity of the universe. Without supernovae, elements crucial for planets and life as we know it wouldn't exist. The heavy elements produced in supernovae eventually become part of a new star system, planet, or even living organism. The calcium in our bones and the iron in our blood were forged in the heart of a dying star, which just goes on to show how life is all surrounded by each other and how everything is interconnected. Now, detecting and observing a supernovae is no small feat. Astronomers use a variety of methods, including optical telescopes, space observatories, and even neutrino detectors. When a supernova occurs, it emits a burst of neutrinos, nearly massless particles that travel at close to the speed of light. These neutrinos can be detected by specialized instruments like the Super Camino Cand in Japan, providing an early warning of the supernova event. Optical telescopes, both ground-based and in space, capture the light emitted by supernovae. By analyzing the light curves, which show how the brightness changes over time, and the spectra, which can release the chemical composition, astronomers can then determine the type of supernova and the physical processes involved. Now, neutrino observatories like Super Camino Cand and IceCube play a crucial role in studying supernovae. These detectors are buried deep underground or in ice to shield them from cosmic rays and other background noise. Now, when a supernova occurs, it releases a flood of neutrinos. Detecting these neutrinos gives astronomers a heads up that a supernova has occurred, often before the light from the explosion reaches us. This early detection allows for prompt observation with optical telescopes. Now, let's move on to optical telescopes such as the Hubble Space Telescope and the Very Large Telescope, which capture the visual spectacle of a supernova. By monitoring the light curve, which shows how brightness changes over time, astronomers can infer important details about the explosion. The light curve of a Type 1a supernova, for example, has a characteristic shape that can be used to measure distances across the universe, a technique known as standard candles. Now, spectroscopy is another vital tool. By splitting the light from supernova into its component wavelengths, astronomers can determine the chemical composition, temperature, velocity, and other properties of the ejected material. Spectral lines reveal the presence of elements like hydrogen, helium, oxygen, and silicon. By analyzing these lines, astronomers can then classify the supernova and understand the physical processes that occur during and after the explosion. Now let's move on to some case studies. Let's look at some famous supernovae. SN 1987A, for example, was the closest supernova observed in modern times. Located in the Large Magnetic Cloud, it provided invaluable data on the explosion mechanics and the aftermath. Now, SN 1987A was unique in several ways. It was a Type 2 supernova, resulting from the core collapse of a blue supergiant star, rather than the more common red supergiant progenitors. The early detection of neutrinos from SN 1987A confirmed theoretical predictions and provided a wealth of data for astrophysics. Another notable case is Kepler's supernova, which was observed in 1604, and it was the last supernova seen in our galaxy, and its remnant continues to be a rich source of scientific information. And this supernova was a Type 1a supernova and has been extensively studied to understand the explosive mechanisms and the nature of its progenitor system. Now let's move on to its impact on the universe. Supernovae play a crucial role in the cosmic ecosystem by recycling material and enriching the interstellar medium with heavy elements. When a supernova explodes, it disperses elements like carbon, oxygen, and iron into space. These elements eventually become part of a new star system, planet, and even living organism. In a very real sense, we are made up of star stuff. I know, it's amazing. Now, supernovae also play a pivotal role in star formation. The shock waves from supernova explosions compress nearby clouds of gas and dust, causing them to collapse and form new stars. This process, known as triggered star formation, helps regulate the rate of star formation in galaxies and influences the structure and evolution of galaxies over time. Now, supernovae are key players in the evolution of galaxies, as I mentioned before, because they inject energy and large momentum into the interstellar medium, driving turbulent motions and influencing the large-scale structure of galaxies. Now, to look at the future of supernovas, we have to talk about multi-messenger astronomy, which combines observations of light, neutrinos, and gravitational waves, and is opening up new frontiers in supernova research. The detection of gravitational waves from emerging neutron stars and black holes have already provided new insights into the lives and deaths of massive stars. Future detection of gravitational waves from supernovae could also reveal new information about the explosive mechanisms in the formation of neutron stars in black holes. Now, the study of supernovae is a vibrant and rapidly evolving field with many exciting discoveries on the horizon. As we continue to develop new technologies and techniques, we'll gain deeper insights into these powerful explosions and their role in shaping the universe. By studying supernovae, we're not just learning about the death of stars, we're uncovering the processes that create the elements essential for life, the dynamics that drive the evolution of galaxies, and the mysteries of the universe itself. Now, supernovae are one of the most spectacular and informative events of the universe. They not only illuminate the night sky, but also illuminate our understanding of the cosmos. They are the universe's way of recycling matter, creating new stars, and forging elements that can make life possible. As we continue to study these magnificent explosions, we'll undoubtedly uncover more secrets about the universe and our place within it. Now, as I wrap up this episode, I just want to thank you all for joining me on this cosmic journey. If you enjoyed this episode, please subscribe to Following Science, leave a review, and share it with your friends. I'd love to hear your thoughts on supernovae and any questions you might have. So let me know. And also, who knows, your question might be featured in our next episode. Until next time, keep exploring, stay curious, and keep following science. This is your host, Rutu Ruparel, signing off.